Yeah. Okay, so the title of my talk, I'm going to immediately change it. I'm going to call these naive vector bundles on metric graphs. So my construction is going to be somehow extremely elementary. So for a grown-up, cynical view of vector bundles on tropical varieties, you should attend Diane's talk. Okay, so I'd like to thank all of you for coming, and I'd also like to thank the organizers for inviting me here and giving me a chance to speak. Before I explain what this is, oh yeah, this is all joint work. So these are two projects here, one with Andreas and Martin, and then another project with Andreas, Arne and Martin and myself. So let me kind of explain a little bit of the backstory of this project. I converted to tropical geometry a few years ago. So I was working on, my background is originally in soliton equations and mathematical physics. But then I met Martin and he helped me to see the light. Anyway, so at that time I was reading these papers by a group of mostly Japanese mathematicians who were working on tropical integrable systems. So these are kind of discrete evolutionary equations which arise by means of a tropicalization procedure from certain exactly solvable discrete equations. And I was trying to they were obviously a little bit hard to read, and I was trying to read those papers and more specifically understand the geometry behind the constructions. So I wanted to construct a kind of a tropical Kirchhoff correspondence, tropical spectral curves, and so on. And so an important ingredient that was missing is the notion of a vector bundle on a tropical curve, that is to say, on a metric graph. So I asked Martin what that could be. We started talking, and long story short, this is the result of what we came up with Martin and with Andreas. Okay, so again, just to show you how naive our approach is, let me remind you what a vector bundle is. Specifically, let me remind you how to construct vector bundles as check cocycles. So if X is a manifold, and you have an open cover of it, then to construct a vector bundle, all you need to do is choose some transition functions, G alpha beta, from the pairwise intersections into GLN of, well, I don't know, whatever. Maybe this is a real manifold. So these are going to be C infinity transition functions. And so they need to satisfy, well, what relations do they have to satisfy? So maybe G alpha alpha is the identity. And there's also a cocycle relation. So G alpha beta, G beta gamma, G gamma alpha is the identity. And so this means that this tuple of transition functions gives you an element of the non-abelian cohomology set, values in GLN, and so this gives you a vector. Okay, so basically what we want to do is try to mimic this definition for, okay, how does this work? For metric graphs. Okay, maybe I'll just do that. All right. Oh yeah, right. This is actually my first chalk talk since the pandemic started, so it's been a while. So what is a metric graph? Well, a metric graph is just a graph whose edges have been equipped with some real lengths. So this is an example of a metric graph gamma. So the genus of a graph is the number of edges minus the number of vertices plus 1. So this is the graph of genus 2. So it's a metric space, but what's important for us is that it's equipped with a sheaf of piecewise linear real value functions with integer sloping. So F is a sheaf of are valued functions with integers. And so before I forget, pretty much everything that I say works in the category of spaces that have this sort of shape on them, which are called rational polyhedral spaces. In particular, there's upcoming work about all of this on abelian varieties. So on abelian varieties, you can also study vector bundles. And correct me if I'm wrong, the authors are Andreas, Inder, Markberg, and Martin. Is that right?
Actually, I'm at the Vienna. Sorry.
Oh, I'm so sorry. My apologies. I know this only. I haven't actually seen the paper. I've been told that this is also the on the right. Okay. All right.
And it's linear functions.
Oh yeah. So these are, well, that's kind of a piecewise linear function. Functions with integer slopes. Okay, so if you have such a function defined on an open subset of your curve of your metric graph, you can define its divisor as the sum over all points in U of the, well, you could either take the incoming or the outgoing slopes. I'll take the outgoing slopes. At P times P. So this defines for you. Okay, what do I do now? I go back? Yeah, I'll go back. Right.
Oh, you can use the backward.
Like I said. Oh wow. So with an appropriately chosen topology on your graph, this map that takes the divisor of a function is a map of sheaves. So there's a short exact sequence of sheaves. So F goes to div. And so the kernel, so this is the map that takes the function to its divisor. The kernel is the shape of harmonic functions on your metric graph. And so you should think of this as being the tropical equivalent of the, well, whatever this sheaf sequence is called. So this is O star of gamma, and this is M star of gamma. So these are kind of the holomorphic functions, and these are the meromorphic functions on your metric graph. Okay, and so now you can give a definition, and this goes all the way back to the paper of Mikhalkin and Zakharov. Which is, I think, 06, is that a line bundle on your metric graph is an H-torser. So a line bundle on gamma is a torser over this sheaf H. And so the set of line bundles is classified by the cohomology group H1 gamma H, which I'm actually just going to go ahead and compute for you. So if you look at the long exact sequence here, you've got H0 gamma half, then you've got H0 gamma div, H1 gamma H, And then you can prove that, just as in the algebraic case, the H1 of the meromorphic functions is 0. So these are the globally defined affine functions on your metric graph. So these are also just called the rational functions on gamma. And these are the globally defined divisors. So this is just the divisor group. So H1 of H is divisors modulo principal divisors. So exactly as in algebraic geometry, all divisors modulo those that are divisors of rational functions. So this is also called the Picard group of your metric graph. And it is non-canonically isomorphic to the Jacobian of your metric graph times the z, which is called the degree. And so this guy is a g-dimensional real torus. So it's isomorphic to R of the G mod Z. Okay. So the picture for line bundles, that is to say vector bundles of rank 1 on metric graphs, is about as nice as you can imagine. It's kind of a direct copy of the what happens in algebraic geometry. Okay, so now I want to define vector bundles on metric graphs. You just swap the boards. Swap the boards. All right, I'll try that. Okay. So the idea is very simple. These functions take values in R, and I'm going to think of R as being GM over the tropical semifield. So in other words, this is GL1 of T. So T is the tropical semifield. It consists of R with infinity added. Tropical addition is taking the minimum. And tropical multiplication is the usual sum. Okay. So the identity element for addition is infinity. The identity element for multiplication is 0. Okay. Oh, okay, well, I have some room here. So you can take the matrix, you can take matrices over any semi-ring because matrix multiplication does not involve subtraction, right? So I'm just going to define GLMT to be the group of invertible n by n tropical matrices. So this is the set of A in matrices n by n over T, such that there exists a B such that A times B is B times A is the identity matrix. And so what's the identity n by n matrix? That the matrix that has zeros on the diagonal and infinity everywhere else. All right, so that's going to be my group. And so you might be wondering, what is this? So it's a pretty easy exercise to compute what this group is. The earliest known reference I know is a paper of Allermann from 2012, which says the following thing, that a matrix of GLN is a generalized permutation matrix. So GLMT consists of matrices of the following kind. So P sigma times the diagonal matrix, where sigma is just a permutation on elements, and so that's the corresponding permutation matrix. And these guys are real numbers, non-zero tropical numbers. So in other words, this is a semi-direct product of Sn with R. Okay, so if you want to throw up your hands in frustration and maybe walk out of my talk, this would be an appropriate moment to do so. Because clearly this group is kind of not what we had in mind. Right? So the problem is that the dimension of this group is n, not n squared. Are you're all going to stay? Okay. Anyway, so obviously the kind of vector bundles we construct are going to be a small subset of all of the vector bundles that really should be there, because we're looking at a much smaller structure group than we are in the algebraic set. Okay, but if you're going to stay, let's see how far we can get with this definition. And the answer turns out we can get, somewhere. All right, so now, what am I going to do? I'm going to this goes all in. And so what I can do is I can consider the sheaf Sn semi-direct product harmonic to the n. So this I can think of as a sheaf of harmonic GLNP valued functions on my metric graph game. And so my definition is that a vector bundle is just a torsor over the G. So a vector bundle on gamma is an Sm semi-direct product Hn torsor. Okay. So I've converted the tropical geometry, but I retain a number of pagan superstitions from my background as a Russian mathematical physicist. I don't believe in anything unless you write it down in local coordinates and transition functions and so on. So that's what I'm going to do. All right. So what I want to do is I want to define a vector bundle E via a Chekhov cycle. And this is actually really easy to do with graphs because they have such a simple structure. So first, what you do is you pick a simple model for your graph. So that means that you're not allowed to have multiple edges between two vertices. You're not allowed to have loops. So I'm going to need to split this edge and this edge, and I think I don't need to split this edge. Now that's a simple model, right? Yeah. Okay, so there you go. And so then I can pick a canonical open cover associated to this model. So the cover is going to be it's going to be indexed by the vertices of my graph, where UV is just kind of a star around V. So it's the vertex together with all of the adjacent open edges. And so the advantage to this is that if you take the intersection of two such open covers, that's either an edge between those two vertices if there is such an edge, or it's empty. So this is either an edge if such an edge exists, or it's empty. And what's cute here is that triple intersections are empty. So there's no co-cycle condition to verify. Okay. And so, well, okay, I'm going to have to start erasing something. A vector bundle on a metric graph is just given by a GLNT valued harmonic function on each edge. So a vector bundle E on gamma is given by functions GE from edges 2 GLNT for each edge E. And this is semi-direct product. Let me just say what these functions look like. So GE is a tuple consisting of a permutation together with a collection of harmonic functions. But a harmonic function on an integral is just an affine linear function. So GIE of x is AIE x plus BIE, where AIE is an integer and BIE is a real number. Okay, so this is the data that defines a tropical vector bundle on a metric graph. Okay, so what are some standard operations you can define? There's quite a few. You can define direct sum. You can define tensor products. You can define duals. Then I guess I should say that if you have a matrix A in GLN of T, its determinant is just a matrix in GLNT has a a unique finite entry in each row and column, and the sum of those entries is the tropical determinant. This is the sum of the finite entries. And so, given a tropical vector bundle, you can define a line bundle, which is the determinant line bundle. And you can just, in terms of the cocycle, you just add together these functions, and that gives you an H cocycle. This is just the line bundle defined by the cocycle Gn. So you can define the degree of a vector bundle, which is the degree of the determinant line bundle, which is just the sum of the slopes of all of these guys. You can also define slope, not to be confused with the slope. This is the slope in terms of stability. So this is the slope U of E, which is the degree over the rank. Okay, and so now you can try to kind of pick your favorite theorem, favorite result about tropical vector bundles about vector bundles on a Riemann surface, and see if they can if they have a tropical analog.
What if my Henry theorem has symmetric or
Has what?
symmetric powers or other two functions?
Symmetric powers. Yeah, you can define symmetric. Yeah, you can define symmetric powers.
You mean you can?
Well, one can. We didn't do it. You can do it now.
Wait, I mean, you can do it for all of your functions. You just do it locally in blue.
Yeah, because hold on. Yeah, just choose a base. Yeah, you can do that. Choose a base. Okay, I'm a little hesitant because you see this. He has kind of characteristic one, so there's. I think the answer is yes, but let me not give that a confident yes. Okay. It's certainly something we didn't write down. I don't know, Martin, do you have it?
I mean, probably gonna work. No. We should write it down before we make 100% statement.
Yeah. Okay. So the first thing I want to talk about is stability. And it turns out that everything is very simple, or perhaps I should say everything is very semi-simple. Okay, before I give a definition, let me give a very simple proposition. Is that any subbundle splits. So if you have E as a subbundle of F, then F is the direct sum of E and something else. This is because a generalized permutation matrix, which is block triangular, is automatically block diagonal. Nothing deep here. Okay, so now I can give a definition. I can say that a vector bundle is semi-stable. If for any subbundle is non-trivial, the slope of F is either strictly less or less than or equal to the slope of E. And so then for tropical vector bundles, due to some simplicity, you have kind of a very simple description. So stable is the same thing as indecomposable. And semi-stable is the same thing as being a direct sum of indecomposable bundles, all with the same slope. So E is E1 plus EK, and the slope of all of these is the slope of your original bundle. Is that?
Yeah. Use the definition of polystable.
Well, I mean,
yes, but it turns out to be
it's
also
the same
also
as
the
so.
same.
Yeah.
Yeah, that's what I'm saying.
So semi-stable is the same as polystable. Right. Okay. So basically, what this means is that I only really need to understand the structure of indecomposable bundles. So now I want to understand sorry, what is it? Indecomposable. It feels really wrong to write M and then not to write G. Right? So these are vector bundles which are stable. Degree is E, and the rank of E is N. Okay, so that's what I want to do now. And so we can describe all of these quite explicitly in the following way. So if I have a vector bundle, so an Sn semi-direct product Hn torser, I can strip out the harmonic part and leave only the permutation. So if I have E, which is an Sn semi-direct product Hn torser, so it's defined by the cocycle sigma E and then GEI. I can just forget about these. I can look at the sigma E, and this gives me an Sn torser on gamma, which is this, well, it's not the same thing, which defines a degree N covering. Gamma tilde over gamma. Do I still have my curve? I don't know. Let me just draw a covering. So maybe if this is your graph gamma, then a covering space might look something like this. There we go. That's a degree 2 covering. And then what we do with these GIs, what they do is they lift to a line bundle on G tilde. Call it L. And then in a way that can be made precise, your vector bundle is just the push forward of this line bundle. So every tropical vector bundle on a metric graph is the push forward of a line bundle. The degree of E is the degree of L. Then the equivalence here corresponds to equivalence here modulo automorphisms of the cover. And then a line bundle splitting sorry, a vector bundle splitting is equivalent to the curve, the covering being disconnected. Okay. So if we want to describe the stable, the indecomposable covers, we only look at connected covers. So M indecomposable M, see, M and of gamma is a disjoint union over all connected degree and covers gamma tilde to gamma of, just take a line bundle on your curve. And then you have to quotientify the automorphisms of the cover. Let's compute the dimension of this space. So the real dimension of M indecomposable and d gamma is the dimension of the Picard, so that's the genus of gamma tilde. And by the what is it, the Riemann-Hurwitz formula, this is M times g minus 1 plus 1. And that's certainly not n squared g minus 1 plus 1, which is the dimension of the moduli space of semi-stable vector bundles on a Riemann surface of genus G. So if you want to throw up your hands in frustration and walk out, it's too late, because this formula is doing its best. The problem is that this n is the dimension of GLMT, right? So the reason we have such a small moduli space is because we have a small structure group. Okay, so this is the bad news. The good news is that a certain number of results that have a certain number of algebraic results can be tropicalized in a exact way. So let me go through a few of them. So first of all, let's take the case of a genus 0 curve. That is to say, gamma is a metric tree, which means that the fundamental group is trivial, which means that there are no non-trivial covers. Any cover is trivial. Which means that any vector bundle splits as a direct sum of line bundles. So any vector bundle is a direct sum of line bundles, which is the tropical version of the Birkhoff-Grothendieck theorem. Okay, let me give you another example. So it's not so hard to prove the following statement, that if E is a vector bundle of rank n but degree 0. Sorry, if it's a vector bundle of rank n, then it is semi-stable of degree 0. If and only if I can choose the transition functions to be constant and not just linear. So if and only if E has transition functions what did I call them? EI, which are constant and not just harmonic. So if you squint at this hard enough, this is kind of like a version of the statement that a semi-stable bundle of degree 0 was one that has a unitary flat connection. And so, you know, I'm thinking of, I don't know what tropical UN is, but I'm going to say that maps to tropical UN are the same thing as constant maps to tropical GLN. So this is some sort of, I don't know, Liouville's theorem going on. Anyway, so maybe this is nifty, but not really deep. Let me give you one example that does actually have algebraic significance, and this is the case of a circle, so a curve of genus 1.
Wait, just before you erase it. So this description of this moduli space is not necessary. It's not how you wrote it. It's not a simplicial complex, right? Because pic D is not.
Why not?
Simplex.
Why is it not a simplex?
We not canonically.
Yeah, you have to subdivide it to get a simplicial complex structure of this
Yeah,
moduli.
sure, yeah.
Yeah.
But it's a, I mean, it's a rational polyhedral space. You can.
Okay. Do you have a canonical subdivision to make
No.
it a simplicial complex?
Pick D? No. There's a canonical subdivision in, what is it?
Pick
In
D.
G, right? But that's a different story.
What are the G tilde axes?
Yeah, or in the genus, but that's. There is a canonical subdivision of the translation. Oh. Okay, so let's say that gamma is a circle, and the genus is therefore 1. And then for any n greater than or equal to 1, there is a unique connected cover. So if this is my gamma, then gamma tilde is also a circle of n times the length. And so this is my cover of degree n. And so, therefore, MND, indecomposable, is the Picard group in degree D of gamma tilde modulo the automorphisms of the cover. So for a metric circle, its Picard group is a torsor over pic 0, which is the circle itself. So this is just gamma tilde over the automorphism group of F. But if you take this cover and you quotient by the automorphism, what do you get? Well, you just get the curve downstairs, right? So this is a tropical version of Atiyah's classification of indecomposable vector bundles this is Atiyah trop, right? The classification of indecomposable vector bundles on the elliptic curve. And we can also classify semi-stable vector bundles, which is a result of 2, which is kind of in the algebraic setting as a result of 2. There's. So if you have a semi-stable bundle, that means it can have several connected components, but all of them have to have the same slope. So now I want to construct MN D gamma. So these are the semi-stable bundles. So if I have E in here, then E is a sum of indecomposable vector bundles. And so the rank of EI all of them have to equal the rank of E. So if you think about this, sorry, not the rank, the slope has to, mu of EI has to equal mu of E. So if you think about this for a second, that means that the rank is n prime times ki, and the degree of EI is d prime times ki. So here, what I do is I take h, which is the greatest common divisor of n and d. N prime is n over h, and d prime is d over h. So basically, for every partition of h, I have a pattern of splitting my vector bundle. So K1, sorry, K1, oh, that's not great. Let's call this L. K1 through KL is a partition of H. And each of these is now just a copy of the curve itself. Okay. So I get the largest dimensional component for taking a partition all into ones. And so what I conclude is that MND gamma has a top dimensional component, which I'm going to call MND main of gamma. And so this is just the H-fold symmetric power of my curve. And then there are a few components which are also symmetric powers, but of lower dimension. So there's a disjoint union of smaller sims. And so this is the tropical analog of Thu's classification of semi-stable vector bundles of an elliptic curve, where he proves that the H-fold symmetric power. Okay, so I think I should say at least something about algebraic geometry. This would be a good moment. Let's talk about tropicalization. Let's just stare at this formula for a second. When is n times g minus 1 equal to n squared times g minus 1 plus 1? Well, so this happens in one of two cases. Case number one is n equals 1. So this is can we stay here?
But somebody else comes.
All right. So this is the case of line bundles. And the tropicalization of line bundles, this is a paper of Baker and Rabinov. From 15, which is kind of that tropical line bundles tropicalize as nicely as you want. So if you have a curve X, smooth curve over a non-Archimedean field, you can construct the Berkovich analytification. Then the Berkovich analytification retracts onto the skeleton of the Berkovich analytification, which is the tropicalization of your curve. And then they prove that the skeleton of the Jacobian is the Jacobian of the skeleton. So if you look at the Jacobian of your, sorry, let me get this right. If you look at the analytification of the Jacobian of your curve, then it has a skeleton which is isomorphic to the Jacobian. This is the tropical Jacobian of the tropical curve, which is the skeleton of X. And so this isomorphism is respect to the Jacobian bending on both sides. So X and sigma, and here you've got just gamma X. Okay. But of course, the other case when these two formulas agree is if G is equal to 1. And so it turns out that for yeah, I want to leave this on the board. Vector bundles over curves of genus 1 also tropicalize nicely. So now X is a tape curve over K, so its genus is 1 and it has semi-stable reduction. And then we proved, and when I say we, I mean Andreas and Martin proved the theorem that oh, am I kidding here? That if you look at M and D X, so these are semi-stable vector bundles of rank D degree and degree D. What happens is that all of these vector bundles can be constructed by taking push forwards of line bundles along various isogenies of elliptic curves. And we can tropicalize all of the components of that construction. We can tropicalize maps, we can tropicalize line bundles. So all of this tropicalizes. So if I take X, this space, and I take its analytification, it has a canonical strong deformation retraction onto its skeleton. And D of X. And this thing is isomorphic to precisely this main connected component, sim gamma. So this is main, oops, sorry, M and D main gamma X. So this thing is the H-fold symmetric power of gamma X. And this by essentially a kind of a result of, essentially by the result of 2, this is the H-fold symmetric power of the analytification, where H is the greatest common divisor of M and D. Now, our naive theory gives you, works for rank 1, which is already known, but also in genus 1. Okay, I have 12 more minutes left. Now I want to talk a little bit about a different project.
Isn't this square? I mean, you also can have a reflection of the symmetric power of this end.
Yes, yes. So this is yeah. So this is Madeline Brandt and Martin. They look at tropicalizations and so yes. So this map also respects this.
Okay, so this commutes.
Yeah.
Okay.
I mean, there's probably a choice of point involved somewhere, so. Yeah, you have
the big curve there's always.
Yeah.
The 0 point.
So if you have an elliptic curve, yes, so you have a 0 point, and then you can just choose it. All right. So what I want to talk about is something maybe even more naive than what I started with. I want to talk about other Lie groups over the tropical semifield. And here I have to make a little, it's not a disclaimer so much as an appeal. If you or one of your friends has done this before, please let us know, because this is kind of, we haven't found anything like this in the literature, but we wouldn't be surprised that people have thought about this. Okay, so Lie groups over the tropical numbers.
Before you continue, there's a question in the chat. Do you have concepts of sections of vector bundle or something such as Riemann-Roch or anything?
So there you can construct the answer is you can construct a total space of your vector bundle just by gluing together copies of T to the N along the transition maps. You can look at sections of that. And there is a Weil-Riemann-Roch theorem, which is see if I can get it. Rank of E minus rank of the canonical tensor E dual is the degree of E minus n times sorry,
N times G.
no, n times g minus 1, yeah. Where the rank of a vector bundle you can just define as the Baker-Noreen rank of any line bundle that represents it on a full vector. So that's, yeah. You have that there. That, I hope that answers the question in depth. Okay, so we have GLNT, which is just semi-direct product of Sn with Rdn. So since we have a tropical determinant, we can also define SLNT, which is just the kernel of the tropical determinant map. So all of these matrices where take the zero hyperplane in this space. You can of course define PGLNT, which is just GLNT modded center. So can you go on? Can you define tropical orthogonal groups, maybe tropical symplectic groups? Okay, so that's what I'm going to do. I'm going to define a tropical quadratic form. And so the way I'm going to do it is I'm just going to take the formula for the standard split quadratic form, which is defined over any field, and take its tropical version. So this is going to be a map QM M T. And there are going to be two different formulas. So if M is 2n, then I hope this is going to be self-explanatory. I'm going to define Q of X bar be the tropical sum of Xi tropical times X minus I, where the index set for my variables is minus n to minus 1, and then 1 to n. And this is I from 1 to n. And then if M is odd, then my index set from my variables is minus n to just all the way to n. And so I take this formula, Q of X, and then I also add, well, X, okay, 2x0. So this 2x0 is x0 tropical squared. Okay. And so now I'm just going to go ahead and define the tropical orthogonal group as the group of invertible tropical matrices which preserve this form. So OM of T is going to be all A in GLM of T, such that, what is it? Q of A of X is Q of X for every X in T to the N. Okay, so that's the orthogonal group. So let's now also define the special orthogonal groups. So to define the special orthogonal groups, you have to look back at how they're defined over arbitrary fields, specifically over characteristic 2. So there you have to be careful. So the special orthogonal group for odd, people in representation theory tell me that SO2n and SO2n plus 1 are completely different objects, and they shouldn't be denoted by the same letters. Anyway, so SO2n, I'm going to define to be the kernel of the determinant, but any matrix here actually automatically has 0 determinant. So this is just going to be O2n plus 1. But then SO2n over an arbitrary field is defined as the kernel of something called the Dixon invariant, which is, there are many ways to define it. It's the number of factorizations, the number of terms in a factorization of your matrix as a product of reflections mod 2. And so in this case, this is actually an index 2 subgroup of O to N of T. You can define the tropical Dixon invariant and get this thing. And then, so the last one maybe is a little bit surprising. Well, the thing is that you should think of the tropical semi-field has no non-trivial roots of unity, right? So mu k of T is the set of X and R such that Kx is 0. So that's just 0. So in particular, you should think of it as a field of character. It's a field of characteristic 1 somehow. It has, in particular, it has characteristic 2. So in particular, symplectic and orthogonal should just be the same thing. So this is just going to be O to N. Okay. And now homework. Define G2 of T. That's a cool thing to think about. Okay, and so I have what, 3 minutes left? That's four. That's wonderful. Okay, I'll state a theorem, and I think that will be it.
Push all the chords this down, down, down.
And use the
Oh yeah, I
background.
still have like one reserve chord, right?
Yes.
You can use it in the
Sorry? Exactly. That's what I'm gonna do now. Yeah, so that's again, this is for people who think about a F1 geometry. What I'm about to say might be trivial, but we didn't actually find a reference for this anywhere. So here's what I'm gonna do. I'm going to take a root datum. And so this is going to be M R M hat R hat. So M and M hat are dual lattices. Of the same rank. Say rank N. So R and M are dual and M dual are finite subsets. And the Weil group is the finite automorphism group of the lattice. Generated by the reflections in the roots. Okay. So, all right, I had two minutes for definition and now 2 minutes for theorem. Sorry, okay, I have one more definition. Definition. The tropical Lie group associated to a root datum is the following thing. So the Weil group acts on the lattice, so it also, by duality, it acts on the dual lattice. I'm going to take the dual lattice, it's a z to the n. I'm going to tensor it with R and just extend the action. This is going to be Weil group, semi-direct product, dual lattice, tensor over z with R. And then theorem, and this is our new project with, this is part of our new project with Andreas, Arne, and Martin, is that the tropical Lie group of the root lattice of PLN, SLN, PGLN, SO 2n plus 1, SE 2n, and so on, is GLMT SLNT, PGLNT. So all of these constructions can be arrived at in a canonical manner just by taking your lattice and kind of adding real numbers to it. Okay, and just one last thing. You can now say, okay, if this is your group, what do vector bundles with this structure group look like? And the answer is pretty simple. Essentially, what you get is a vector bundle, which is the push forward of a line bundle on a graph that comes with an involution. And that line bundle has to be odd with respect to that involution. I think I'm going to stop.